Would you believe me if I told you there's a way to write data parallel programs in a generic, hardware agnostic and extremely simple way? You probably heard about CUDA, which is a special language developed by NVIDIA that allows you to write data parallel programs in NVIDIA's GPUs. If you don't know what a GPU is, it stands for Graphics Processing Unit. And those kind of devices are really good at processing huge amounts of data in parallel. This means that while your typical CPU has multiple cores, 8, 64, a GPU has up to thousands of cores. Of course, the GPU cores are a little bit different to the CPU core, meaning that they are a little bit slower and they have a little bit less memory. But the fact that you have so many of those in your GPUs means that you can do thousands of simple operations, typical mathematical operations, really fast at the same time. Back to CUDA. The thing about CUDA is that it doesn't really work for devices that are not from NVIDIA usually. Maybe it works, but it might take a little bit of hassle. Although it is a really good programming language, it isn't suited for generic devices. I hereby present you SYCL, the future of heterogeneous programming. SYCL is a framework that allows you to write programs that would work in any kind of parallel computing device, such as GPUs, CPUs, NPUs, FPGAs, you name it. And it also works for smaller devices like a Raspberry Pi or NVIDIA Jetson. So it's really portable, really convenient, and really nice. And one of the best parts of it is that you write a single program and the very same program would work in any kind of different parallel device. So no longer vendor lock, same program, multiple technologies supported, everything in one single package. Excited? A little bit on the backstory of SYCL. SYCL was heavily inspired by OpenCL, which in turn was inspired by OpenGL. And those open standards are a means to establish a common API that is supposed to be implemented by different suppliers of parallel computation hardware, like a GPU. And in 2012, they created the SYCL standard, or the SYCL specification. Then SYCL ended up becoming this much nicer, much more friendly, convenient, and very modern way to interface your application with parallel computation devices. And with the boon of AI and the boon of new kinds of hardware, for example, NPUs or TPUs, which are also in nature parallel, SYCL has been gaining more and more traction and more attention and pushes from bigger companies like Intel. But what exactly is SYCL? Great question. Essentially, SYCL is kind of an extension to the C++ programming language. This means that it requires a special kind of compilation that understands parallel constructs such that those parallel constructs are correctly dispatched to a generic GPU. Basically, you have a C++ program that supports new constructs like queues and kernels, and the compiler understands and compiles program in a special way that it interacts with parallel computation devices. In practice, what would be the step-by-step process that you would have to do to build a program that is SYCL compliant? So the first step you have to do is you pick a SYCL compiler. So you cannot use your standard C or C++ compiler like GCC or Clang. You have to go with a different kind of compiler that understands all the parallel constructs and understands the way you have to dispatch your kernels or parallel programs. The second step is obviously you write a SYCL program. Third step, obviously you run the thing. So in the third step, once you have your SYCL program built, and very importantly, your SYCL runtime is available in your machine, you are able to run the actual program, and the SYCL runtime will interpret and load the program in your GPU. And here's what I think the most powerful thing about SYCL is it doesn't require you to specify anything about your hardware. So basically you write your program, your parallel program that is trying to solve a parallel problem. You don't have to think about hardware. To better explain what SYCL does, I've prepared what I think is a nice diagram that allows you to walk through the process of using SYCL and how SYCL interacts with your GPU. So here we have SYCL at the top, and it takes the form of a compiler. There are different compilers. Each compiler has a different flavor of the SYCL standard, but essentially they all have to do the same job. So I've picked one very nice compiler, which is community maintained, open source, and I like the drive that goes behind the developers, and this one is Adaptive CPP. There are others like the one provided by Intel, which is DP-CPP, maintained by a big company. Maybe it supports more devices. It definitely supports their devices. So you have your SYCL compiler, then you use that SYCL compiler to build your application, and the compiler also provides with a SYCL runtime. This means that while you are building your compiler, you are also at the same time building a runtime that is required by your application. You need a compiler and you need to build the compiler. While you build the compiler, the runtime is also built together. They both are used to build your application. So those are the dependencies in place. Once you build your program, you can tell the compiler to treat the GPU part of it differently. Or you can tell via the compiler that you are building for a specific GPU. So you have many options, you have a lot of freedom to indicate to the compilation process, hey, this is a generic GPU program. So make it work in all the different devices. Let me pick at the runtime, when I run the program, I want to pick at that time which hardware should I use to compute the parallel program. That is an option with SYCL. You don't have to pick, like I said, you don't have to pick beforehand a specific hardware. You can build a generic program, and during the runtime, you can select the hardware, which is, I think, a really great feature of SYCL. The way they made it to work is by using JIT, so just-in-time compilation. And this means that by the time you start the program, you're gonna indicate to which hardware you're gonna build, and that indication will instruct the runtime to build this intermediate representation of your GPU program and dispatch that. And I think that's a great process because it's really flexible, versatile. Although for the first time, let's say you're gonna run a specific kernel, you have a special program. So for the first time you're gonna run the program, you have to just in time compile that program. That takes a time, but the next time you run the same kernel, it's already compiled. So one time you run the program, the runtime builds the GPU part of it, dispatch it, and then that's it. After you call that again, you don't have to build it again. It's already just built, and then it's loaded, and then you actually run the program, the GPU program. The important takeaway is that you write one program to rule all the devices. Ready to see this magical technology in action? Let's get practical. For today's experiment, I've prepared a program that performs an n-body simulation. So a number of bodies exerting gravitational influence on each other. And by now, perhaps you can already imagine why this can be a parallel problem. Can you? So starting with two bodies, you have body A and body B. If you want to compute the gravitational influence of each other, you're going to realize that A is attracted by B and B is attracted by A. So there's a force AB and there's a force BA. So if I want to compute how much A is going to move, and if I want to compute for B, I do the same, which is the same force. Now, what happens if I add a new body? So two bodies, two equations, or two calculations, but what if I add a third body, so body C? This means that A will be attracted by B and C. So if we cut the number of arrows, this also means the number of calculations has performed. So before, with two bodies, we did two calculations. With three bodies, the number goes up 6 calculations. If you do the math, you're gonna realize that if you add any bodies, you're gonna have to compute n times n minus 1 calculations. And this is a O of n square problem, meaning that the larger the number of bodies, your calculation time grows quadratically. And that can be painfully slow. For curiosity, there are more smarter ways to approach the problem. But for the sake of expressing parallel problems, I think this is a really nice one. Now, can you identify where is the opportunity to parallelize the problem? Sequentially, yes, you have to walk through all the forces one by one. How to parallelize this? Theoretically thinking, but if you have an infinite number of threads, this problem becomes O of n. Because if you have one thread per body, you only have to process the influence from all the other bodies onto yourself. So if I have n threads, my problem becomes O of n. Of course, in practice, there's no such device device with infinite GPU threads, or in SYCL language, work items, to some degree, you can already convert the problem from O of n squared in the CPU, single thread, to O of n, given that your GPU has as many threads or work items as the number of n bodies. And if you have more bodies than threads, SYCL allows you to adapt your problem or your ranges easily. So SYCL, you can use SYCL to abstract even that. And literally you just say to SYCL, hey, give me the parallel, in parallel, give me the influence of everybody independently of each other, and then synchronize. All right, enough theory. What does this SYCL thing look like in the code? Let's have a look. So I'm running this Visual Studio Code IDE in my MacBook. Inside that MacBook, I have the dev container set up. This is a dev container that I built beforehand, and it basically installs SYCL and installs OpenCL libraries that I can use as a device. So this is, and it's based on NVIDIA. So this means that the whole NVIDIA backend is already pre-built as well. So if I would, of course, it doesn't, although it has the NVIDIA libraries, CUDA libraries in my MacBook, it doesn't do anything with it. But if I were to use this Docker image as a base in a device that has NVIDIA, it would also be part of one of the GPUs that I could select by the time I run the application. So there's a Docker file that builds everything, and then I've prepared this Docker file. I pushed in the Docker Hub, and from there I can fetch this, and this can become my dev container, so with all the dependencies, all the libraries, all the stack that I need to build my SYCL application is already there. If we go back to the main application, so end-body-sim, this is what I'm gonna call, and so it's a simple program. It takes a few arguments as an input. I can give how many bodies I want to simulate and how many iterations. So if I have 10 bodies and I want to iterate over these 10 bodies 10 times, I can give this as an argument to my program. This means that they will be attracted to each other as I iterate over all of them. So here at the beginning, I'm already using SYCL. So here I print what is the device that is actually loaded or picked by my application. And you can have multiple SYCL devices at the same time in a single application if you would create different queues. And each queue is a representation of a pipeline of instructions that you can send to the GPU. What is important is that the queue is your main point of interaction with your GPU. Through the queue, you instruct memory copies, you instruct to which device you're communicating with, you instruct kernel submission, you instruct work orders. By the way, through the video, I've mentioned GPU, but what I really meant is a parallel device. So I'm gonna walk a little bit quickly in the program. You can pause the video if this is too quick, or just slow down, doesn't matter. The way it works is we print the device that is loaded or being used by the queue. I've prepared a special class that inherits an abstracted end body. So this is to capture the common stuff. And the way I've designed this is that I have this end body, two different implementations. I have the GPU or the parallel device body, and I have the CPU body, and I did this, or the normal body, and I did this for us to be able to easily compare what happens if I use one or the other, how much time it takes to compute all the forces and whatnot. This is the abstract body. It contains data, so some floats. It contains basic motion simulations. This is a two-dimensional body simulator, and I've added a few virtual functions that are supposed to be implemented in the child classes. So the CPU body, which is your normal simulator, let's say, is the way you would program a normal C++. You would use like vector push, for example, as a data struct to the body. I've also created the GPU body, and the GPU body does the same, but it does interact with the memory from the GPU. During the construction of the body, I pass the queue. So this means that this is the point where I'm using the SYCL language in my application. I pass it as a queue, and in the queue will allocate the memory, add bodies to this abstracted memory model of my GPU. And I've also overridden update method. And the update, in my problem, the update is a method that's gonna look at the influence of all the bodies, compute all the forces, step over the motion, and update all the positions of all the bodies. This is the heavy duty slow and where the whole processing is. If we look at the CPU implementation, this you can immediately see where the n square nature of the problem is. So there are 2 for loops, one of them to go to all the bodies, and for each one we go to all the other bodies, and then we exclude ourselves because we don't have forces interact with ourselves, and then you compute the update. So compute all the influence of all the forces, update my velocity, update my position, and then go to the next body. This is very slow and time consuming. Looking back at the main program, it's really simple. So I create the 2 kind of bodies. I reserve the same number of elements. I add the same number of bodies. Stopwatch stuff to get the timings. And here is where we do the calculations. So here is where we're gonna look at all the forces, calculate all the interactions, and I do the same call using the CPU. But before we run this, of course, we have to see, okay, you've shown me how the CPU implementation looks like, very slow, ugly. How does the SYCL implementation looks like? So if you go to the end body, GPU, this is how it looks like. So here, we see memory allocation. This is where we reserve the memory. This is where we add new bodies to my memory. This can be made much better, by the way. This is just a simple way, naive way. But here I essentially am tracking how many bodies I add to my GPU memory. Keep in mind that we're using the queue. Remember, the queue is the way to interact with the GPU, and the queue is an object that allows you to either wait or not for commands that you send to the GPU. So could have actually removed this possibly, just instruct the queue, hey, keep adding bodies, and just put the wait before the calculation, meaning that I'm not too concerned at the time I call this, I'm not too concerned this has to occur. So with SYCL, with the queue, you can actually do a lot of asynchronous programming. So you don't have to wait for everything in the GPU, hand over the execution time back to you. You can actually dispatch a lot of stuff and only wait whenever you really need the results or you really need the memory separated. And now the magical stuff. With the queue and SYCL, we can call something called parallel for. Parallel for is what you're telling your application, hey, run the same program, this many threads or work items as much as you can. So this is where the hardware is abstracted a little bit. So it doesn't matter if your hardware has this many threads. What matters is that you want to parallelize the computations of all these n bodies and leave the implementation of SYCL to take care of the details. So here in parallel, I just want to calculate all the bodies of all the influences of all the bodies on each other in parallels. And the way it works is each thread is going to get a unique index. This computation right here is done in parallel. My GPU is invoked a number of bodies, threads to work in parallel, and each one of them is going to execute this piece of code. And that's SYCL. A very important remark to make here is that SYCL allows you to program in a high-level way. So this body, that is a body from the GPU, this is a representation of a body in 2 dimensions, and this is an object. So what I'm actually doing is I am uploading or putting in my GPU an object in a high-level language. The methods are also, you can also call the methods in the GPU. So what I'm trying to say is that you actually just program a function as if you would normally, and SYCL takes care of compiling that to the language that the GPU understands. This is plain C++, and I'm actually calling from the GPU the same function. This update function is a function given like this. I really think this is really cool. So back to my SYCL program, my parallel program, notice that once we compute in parallel all the forces of all the bodies on ourselves, let's say, I then have to compute the influence. So I add up all the forces, so I calculate all the forces, but then I have to actually, then after everything is calculated, this is the time that I want to update the velocity and the position. So if I don't add this dependency of execution, if I calculate the motion in parallel as I compute the influence of the forces, this can lead to very nasty race conditions. So I have orchestrated in a way that those have to be explicitly done in sequence. SYCL allows me to be explicit about this as well, because in the second submit, I can say, hey, first do the compute forces, so compute all the influences, then I update my state. And then of course here I wait. By this time the execution of the program is handed over back to the host and I've finished my computation. Just to be clear, in SYCL terms, whatever you put inside the Parallel 4 is what is called a kernel. This is what is definitely gonna be converted to GPU code. Whatever you see in the Parallel 4, this is the parallel execution thing that you're gonna run in parallel in your parallel device. All right, let's run it. Putting this up, I'm gonna build it. I'm using CMake as my build system, and in my CMake, I indicate use the adaptive CPP, which is this SYCL compiler adaptive CPP. So this was built before, and I tell CMake use this and do not use GCC or Clang. So my program is built. I'm gonna run it and body sim. Request number of elements, number of iterations, and the device. I want to run 1,000 bodies 10 times device 0. This is the device. It's a TBB implementation of OpenCL, which comes together with the Docker I built. This is a parallel computation device. It essentially uses all the cores of my CPU as parallel work computation units. You can actually print this. So there's 11 cores, and this means I have 11 to share my loads, my parallel load. 1,000 bodies difference is not too big. What if we do 10,000 bodies? And notice that the kernel was already compiled from my previous run. So there is no overhead yet, but if you would run the kernel for the first time, so this little kernel here, for the very first time you would see a warning in your runtime saying, hey, I built this just-in-time binary of your program. Next time you run it, you don't have to build it anymore. So here you see roughly 3 times the difference, and the difference grows as the number of bodies increase. So here's 10,000, let's try 50,000. So for the GPU, it took 10 seconds to compute 10 times 50,000 bodies. The CPU is taking longer. All right, so we got 4.3 times faster computation of this body problem in a GPU compared to the CPU. Just by changing the device, you can actually use a different implementation of backend. And here you see the warning. So I'm no longer using TBB. I'm actually now using OpenMP. This is what comes together with when you build the adaptive CPP backend. Important is that we can actually switch the device on the fly, on the runtime, roughly the same time. Now I said before that we could actually use the same program in different architectures even, as long as they have a SYCL runtime deployed. And that's the case for a Raspberry Pi that I had here. So this is a terminal for my Raspberry Pi, and I'm actually gonna just copy as is from my MacBook to a Raspberry Pi, which is also ARM64. This is why it works, and I'm gonna run the SYCL thing from my Raspberry Pi. So and I've copied that, and now the application is here, and this is a Docker inside the Raspberry Pi with all the SYCL dependencies already built. Adaptive CPP runtime, so I can actually run the simulator. And if I look, for example, the libraries that it loads, this is the runtime. SYCL comes together with the compiler. So let's run it. I'm gonna add 10,000 bodies, 10 iterations, device 0. Device 0 is the OpenMP implementation, and immediately we see the benefits. And this is slow because I only run it once, so if I run it twice, there's no more compilation needed for the kernels, and I benefit from the throughput of my GPU. So this is, I think, almost 3 times. If I do double the amount, so GPU took 5.6 seconds. We're using the only 4 cores that we have in the Raspberry Pi, while the host, using the single core of the CPU, way longer. Almost 4 times, a little bit less. So that's cool. But I want to see in a real GPU. So far we have been using only CPU devices that were like represented as a parallel device, which is fair. They have multiple cores and execution units. But I want to see in a real NVIDIA GPU, for example, how is this program going to be? So this is a Docker. This is another laptop that I have. It has a GPU, dedicated GPU, NVIDIA GPU with a lot of memory and a lot of thread. What if I upload my program here? I cannot actually do this. I have to use a container with a different architecture. So this is AMD 64, and I'm gonna rebuild the container so that I produce binaries that are in the same architecture of my target device. So I'm gonna build the same application. Now I'm building from my MacBook to x86 using platform AMD64 Linux base. It's gonna be a little bit slower, but I still gonna produce the binaries compatible with my target architecture. It's finishing the build. All right, so my application is built. Can I run it locally? Yes, I'm gonna upload this program to my, all right, back to my NVIDIA device. I have the program here, let's run it. 10,000 bodies, 10 iterations, device 0. We no longer see the complaints about missing NVIDIA, we see complaints about missing OpenCL, but that doesn't matter. So I'm still using the OpenMP, but I'm gonna select another device. And now I'm actually using NVIDIA compiled SYCL kernels. So don't mind the warnings. Notice how fast it is already. So this is the CPU and this is the GPU. What if I do 50,000? See how much faster is the GPU now. And it's finally over. So it took roughly a minute. Look at how much more time it took to run this compared to the parallel GPU, which is actually an NVIDIA device. And of course, if I were to compare with the core, so this is a laptop which has 28 cores, we're still gonna see a lot of benefits by parallelizing the problem, distributing the problem in my different cores. So yeah, not as fast as the CUDA NVIDIA device, but still tons of times faster than the CPU. And that concludes the video. I really hope you have learned something new. This is a topic that I enjoy a lot. Thinking parallel, thinking how to parallelize, how to squeeze the absolute maximum capabilities of computation devices. This is something I really enjoy doing, and having a tool like SYCL that facilitates parallel thinking and parallel computation, parallel access to your parallel device, I think that's a really great advantage and benefit that it provides to you. Thank you very much for watching.